Land use changes around Lake Jackson have neighbors there wondering and worrying about the impacts on the environment and the look of their community.
It happens in less time than it takes to drink your morning coffee. One night, there is a 4,000-acre lake glittering under the stars, full of bass and bluegill, ringed by docks and porch lights. By sunrise, there is nothing but a smear of gray mud, stranded boats leaning on their hulls, and a black hole in the earth swallowing the last of the water with a sound like a bathtub drain the size of a football stadium. This is not science fiction. It has already happened more than once in the same Florida lake, and the pattern behind it is now being watched more closely than ever, because the same forces that can empty a lake overnight can just as easily threaten the drinking water of an entire city. Stay with me, because what's happening under the ground here is stranger and more consequential than almost anyone living above it realizes. The lake at the center of this story sits just north of Tallahassee, Florida's capital. For generations, locals have simply called it Lake Jackson, but its older name carries the real warning. The Appalachian people who lived along its shores centuries before European settlement called it Okeechobee, disappearing waters. They didn't need seismographs or satellite data to know what the lake would eventually do. They watched it happen with their own eyes over and over, long before anyone built a subdivision on its banks. To understand why a lake can simply vanish, you have to stop thinking of Florida as solid ground. Picture instead a giant block of limestone, hundreds of feet thick, riddled with tunnels, chambers, and hairline cracks. Something closer to a sponge than a slab of rock. This porous limestone foundation is what geologists call karst terrain, and it formed over millions of years when the entire peninsula sat beneath a warm, shallow sea. The shells and skeletons of ancient marine life piled up on the seafloor and compressed into limestone. When the sea eventually withdrew and exposed the land, rainwater began doing something limestone is uniquely vulnerable to: dissolving it. Rain picks up carbon dioxide as it falls and moves through soil, turning slightly acidic. That acid is nothing to worry about if it lands on your skin, but given enough time, thousands of years of it, it eats away at limestone, widening tiny cracks into sinkholes, caverns, and underground rivers. Beneath that honeycombed rock sits one of the largest freshwater reservoirs in North America, the Floridan Aquifer, a slow-moving underground ocean of drinking water stretching across Florida, Georgia, Alabama, and South Carolina. Millions of people across the Southeast rely on it every single day without ever seeing a drop of it directly. And at certain points across the state, the barrier between the surface world and that aquifer is thin enough to fail. Lake Jackson happens to sit directly above one of those weak points, a natural drain known as the Porterhole Sink. Under ordinary conditions, decades of leaves, sediment, and organic debris settle into the throat of that sink and pack it tight, like a natural cork. The weight of the lake pressing down, combined with water pressure pushing up from the aquifer below, keeps that plug wedged firmly in place. It's a fragile equilibrium. Heavy rain refills the lake, the plug holds, life on the water goes on as normal. But when a serious drought settles over North Florida, that balance starts to break down from both directions at once. The lake's surface drops as water evaporates, lightening the load, pressing the plug shut. At the same time, the regional water table falls, which reduces the upward support holding the plug from underneath. Eventually, the organic seal simply can't hold anymore. It gives way, and the lake starts draining directly into the earth. This isn't a rare, once-in-a-century anomaly. Lake Jackson has drained partially or completely more than a dozen times in recorded history, sometimes over the course of weeks, sometimes in a matter of days. Locals have learned to expect the way people elsewhere expect a hard winter. Fishermen still remember walking across cracked, sun-baked mud where their boats used to float. Alligators, herons, and vultures descend on the exposed lake bed to feast on stranded fish before the water is gone for good. For centuries, this cycle actually served a purpose. Draining the lake let the sun bake and sterilize decades of built-up muck, and when the rains eventually returned, the lake came back cleaner and more biologically productive than before. It was a self-cleaning system nobody had to build or maintain. The problem is what happens when that ancient, self-cleaning cycle collides with a modern American suburb. Northern Florida today is not the wilderness the Appalachia once knew. Tens of thousands of homes, several major roads, shopping centers, schools, and water infrastructure now sit on top of, or immediately beside, the same karst system that has been quietly draining and refilling this lake for millennia. And here is the uncomfortable truth hydrogeologists have been raising for years. The underground plumbing beneath a growing city doesn't always behave the way it did when the land was empty. Decades of construction compact the soil above certain channels. Storm drains and paved surfaces change how quickly water moves and where it collects. Years of heavier than normal drought stressed the aquifer in ways it wasn't stressed a century ago. When you combine all of that with a natural drainage system built out of caves and fractures rather than pipes and valves, you get something engineers can monitor closely but never fully control. So picture what happens if, during one of these drainage events, the underground pathway that normally carries the lake's water safely down into the deep aquifer becomes partially blocked by silt, by drought-compacted sediment, by the sheer unpredictability of a cave system nobody has ever fully mapped. Water under that kind of pressure does not simply wait for an opening. It searches for one. It can travel sideways through narrow limestone layers instead of straight down, sometimes for miles, following whatever path offers the least resistance. And if that path happens to pass beneath a residential neighborhood, the results can look less like a lake disappearing and more like the ground itself coming apart. This is the scenario now keeping emergency planners and water utility engineers up at night, because Northern Florida is home to roughly 400,000 people who ultimately depend on the same fragile aquifer system that Lake Jackson sits on top of. A serious disruption to that system doesn't stay contained to one lakebed. It can ripple outward through the exact infrastructure that keeps a modern city running. Start with the water utility itself. Municipal systems are built around assumptions of steady pressure and predictable supply, clean water in, treated water out, at a consistent rate day after day. If a major shift in underground pressure damages or displaces even a handful of deep wells, or if a sudden intrusion of sediment fouls a well field, utility engineers can watch mainline pressure drop with almost no warning. Boil water advisories can be issued for tens or hundreds of thousands of residents literally overnight. Fire hydrants that firefighters depend on for water pressure during structure fires can lose the flow they need at the worst possible moment. None of this requires a hurricane or an earthquake. It only requires the ground beneath the pipes to shift by inches. Then there's the threat that worries hydrogeologists most of all, saltwater intrusion. Florida is a peninsula, which means the fresh water sitting in the aquifer is under constant pressure from salt water pushing in from the coast. As long as that freshwater layer stays thick and its pressure stays strong, it acts like an invisible wall holding the ocean back. But drought and heavy groundwater withdrawal can already thin that wall out. Add a sudden localized drop in pressure from an unusually severe or unusually fast lake drainage event, and you create exactly the kind of vacuum that pulls salt water further inland than it would normally travel. Once brine works its way into a limestone well field, it doesn't rinse out the way it would from an open tank. It settles into the porous rock itself. And restoring that well field to usable condition can take years and cost tens of millions of dollars in desalination infrastructure many smaller utilities simply don't have. Agriculture feels this kind of strain almost immediately. North Florida's farms, citrus groves, row crops, cattle operations depend on irrigation drawn from the same aquifer under threat. When regulators have to restrict groundwater withdrawals to protect drinking water supplies, farmers are often the first ones ordered to cut back, sometimes in the middle of a growing season. Crops left without irrigation during a Florida summer don't survive long. Multiply that across thousands of acres, and you're looking at layoffs at packing houses, disrupted supply chains, and real financial damage to rural communities that had nothing to do with the sinkhole itself. And then there's what happens to the ground people are standing on. Removing billions of gallons of water from a karst system doesn't just remove liquid. It removes the hydraulic support that had been holding up the layers of rock and soil above it. Engineers sometimes describe this as pulling the cushion out from under a mattress. Without that support, secondary sinkholes can open in places that had shown no warning signs at all. A crack spreading across a driveway, a door that suddenly won't close right, a soft spot in a backyard that gives way underfoot. Insurance companies react quickly to this kind of risk, sometimes freezing new policies in affected areas altogether, which in turn freezes home sales and rattles local property values. None of this is meant to suggest that a Florida city is doomed to collapse the moment a lake drains. Lake Jackson has emptied and refilled for centuries without leveling Tallahassee. The point is narrower and in some ways more unsettling. The margin between fascinating natural phenomenon and regional infrastructure emergency is thinner than most residents realize, and it's shrinking as drought conditions become more frequent and construction pushes further into karst-prone land. The good news is that this risk is not going unanswered. Florida's environmental agencies, along with hydrogeologists at the state's universities, have spent years building tools specifically designed to see trouble coming before it reaches the surface. Ground-penetrating radar and electrical resistivity surveys let engineers map hidden cavities and fracture zones without ever digging a hole. Fluorescent dye tracing, a technique where scientists release a harmless, brightly colored dye into a sinkhole and then track where it resurfaces, has taught researchers just how fast water actually moves through these systems. The results are humbling. In a typical sand aquifer, groundwater might creep along at a few feet per year. In an open karst conduit, it can travel several miles in a single day, meaning a problem that starts at one sinkhole can reach a well field on the other side of the county in less time than it takes to drive there. Utilities have started responding by diversifying how they capture and store freshwater rather than relying purely on shallow wells that sit close to the surface and close to risk. Managed aquifer recharge, capturing excess stormwater, treating it, and injecting it deep into protected limestone layers, is increasingly seen as a way to build a buffer against both drought and sudden pressure loss, giving utilities a reserve to draw on if a well field near the surface becomes compromised. Land use planning has also started catching up to the geology instead of ignoring it. Newer building codes in karst-prone counties restrict the kind of heavy construction that can be built directly over known high-risk zones, and satellite radar monitoring capable of detecting ground movement measured in millimeters is now used to flag areas that may be quietly subsiding long before anyone notices a visible crack. At Lake Jackson specifically, the management philosophy has shifted dramatically from the mistakes of the past. Decades ago, some engineers tried to simply seal the porterhole sink shut, treating the lake's natural drainage as a problem to be eliminated rather than understood. It backfired, disrupting the lake's ecology without actually solving anything. Today's approach works with the cycle instead of against it. When the lake does drain, state agencies and conservation groups treat the exposed lakebed as an opportunity. Heavy equipment moves in to clear out decades of accumulated muck and invasive vegetation before the water returns, preventing that organic debris from washing straight down into the aquifer the next time the plug fails. Stormwater treatment wetlands built around the lake's edges filter out fertilizer runoff and heavy metals before they ever reach the water. Pressure sensors and flow monitors installed directly in the sinkholes throughout now give real-time data to water managers, so a sudden pressure drop can trigger a response within hours instead of being discovered days later when taps start running dry. None of this makes Lake Jackson or places like it risk-free. What it does is turn a genuinely dangerous natural process into something that can be tracked, prepared for, and responded to quickly. The difference between a controlled inconvenience and an uncontrolled catastrophe. That distinction matters enormously to the 400,000 people who live above this system, because their daily lives depend on infrastructure most of them will never see and rarely think about, built on top of ground that has been quietly dissolving and reshaping itself since long before Florida had a single paved road. Maybe the most important lesson in all of this has nothing to do with engineering at all. It's a reminder of something the Appalachee understood intuitively long before anyone drilled a monitoring well or ran a resistivity survey. The ground is not a fixed, permanent stage that human infrastructure simply gets placed on top of. In Florida's karst country, the earth is closer to a living system, one with its own slow, ancient rhythm of filling and draining, dissolving and rebuilding, entirely indifferent to property lines, zoning maps, or municipal budgets. Modern engineering can listen to that rhythm, adapt to it, and even work alongside it. Sensors in the sinkhole throat, deep well reserves held in reserve for a drought, codes that keep heavy construction off the most fragile ground. What it can't do is switch that rhythm off. So when Lake Jackson drains again, and geologists are confident it eventually will, the story won't be that nature failed the people living around it. It will be a test of whether decades of monitoring, planning, and hard-won lessons from past mistakes are enough to keep 400,000 people's water flowing while the ground beneath them does what it has always done. The lake will very likely fill back in, clearer and healthier than before, just as it has after every previous disappearance. Whether the infrastructure built on top of it can absorb the shock as gracefully is the real question worth watching. If this kind of hidden geological story fascinates you as much as it fascinates us, make sure you're subscribed, because we're only getting started uncovering the invisible forces shaping the ground beneath our feet.